Parked under the harsh glare of artificial hangar lights, the Lockheed C-130 Hercules looks like a relic. It has a blunt nose, a heavy, stubby frame, and 4 massive propellers. It lacks the supersonic swept wings of a 21st century stealth fighter, or the sleek, radar-absorbent composites of a modern drone. This timeline tracks continuous military aircraft production. The C-130 began rolling off the assembly line in 1954. While every other airframe from the Korean War era has been retired, replaced, or scrapped, the Hercules line remains active today. Over those 7 decades, Lockheed has built more than 2,500 of these transports, delivering them to the militaries of 70 different nations. Lockheed has adapted this single-base airframe into over 70 distinct mission variants. Why does an aircraft designed during the Truman administration remain the undisputed backbone of global tactical airlift? Lockheed engineered a universal chassis, a physical foundation so agnostic to its payload that it serves almost any operational requirement. A precise aerodynamic geometry allows the Hercules to function across military, scientific, and civilian domains without structural redesign. In early 1951, the United States Air Force issued a requirement for a medium cargo transport. The directive specified that the aircraft had to haul heavy, bulky combat equipment directly into highly austere, short-field locations. Operating on unimproved dirt and gravel runways presents a severe engineering risk. Engines mounted low on a standard wing will ingest fatal amounts of dirt and debris kicked up by the tires, destroying the turbines. This front-facing cross-section illustrates Lockheed's primary structural solution. By anchoring the wings to the absolute top of the fuselage, the engines are elevated safely out of the debris zone. Securing the wing at the top allows the fuselage to sit incredibly close to the ground. This places the aircraft's internal cargo floor exactly at standard truck bed height, roughly 3.5 feet off the tarmac. Integrating this low floor with an integral aft loading ramp creates a continuous drive-on, drive-off surface. This cutaway reveals the resulting interior volume. The cargo hold measures 40 feet long and 9 feet high, yielding a payload capacity of 42,000 pounds. That unobstructed, pressurized envelope easily swallows 6-wheeled armored vehicles, self-propelled howitzers, 92 standard passengers, or 64 fully equipped airborne troops. All of that capacity can be delivered directly to a dirt strip measuring just 3,000 feet long. By mastering the spatial geometry between the high wing, the low floor, and the aft ramp, Lockheed created an airframe structure that never requires a redesign. Because the core airframe is effectively a fully pressurized flying truck bed, it functions as a structural blank canvas. The Air Force capitalizes on this volume using roll-on, roll-off, or RORO, modular systems. These self-contained pallets allow crews to change the aircraft's entire operational purpose in a matter of hours. Loading specialized RORO fluid tanks instantly converts the standard transport into an aerial firefighter, capable of dropping thousands of gallons of retardant in seconds. Beyond temporary internal modules, the military applies heavy, permanent airframe modifications for specialized combat and scientific missions. The AC-130 gunship variant mounts side-firing cannons and howitzers directly into the cargo bay, transforming the tactical transport into a heavy kinetic weapons platform. The LC-130 Polar variant replaces standard landing gear with massive Teflon-coated skis, enabling heavy logistics support across the ice sheets of the Arctic and Antarctic. The WC-130 Hurricane Hunter is packed with complex meteorological sensors, built to fly directly through the extreme updrafts and eye walls of tropical cyclones. Despite radical differences in these mission profiles, every single variant relies on the exact same base aerodynamic profile and physical constraints designed in the 1950s. This collage maps out the variation, showing how external fuel tanks, sensor arrays, and specialized modules attach to the identical core chassis. A platform that remains strictly agnostic to its payload guarantees its own relevance, easily adapting to shifting military, scientific, and civilian demands. But a structurally optimal airframe eventually faces a strict mechanical limit. By the late 1980s, the analog avionics and internal propulsion systems of the legacy C-130s were severely outdated. Instead of funding an entirely new aircraft design, the military decided in the mid-1990s to completely gut the interior. The result was the definitive 21st century model, the C-130J Super Hercules. This side-by-side performance chart isolates the primary upgrade. Lockheed replaced the legacy Allison turboprops with vastly superior Rolls-Royce AE2100D3 engines. They paired these new engines with highly efficient 6-blade composite scimitar propellers, discarding the old 4-blade metal designs. The Super Hercules generates 29% more takeoff thrust and achieves a 40% faster climb rate than the H model. Logistically, it consumes 15% less fuel while increasing its overall operational range by roughly 40%. Inside, engineers executed a total overhaul of the flight deck, replacing analog dials with a fully digital glass avionics environment and dual head-up displays. This digital automation manages engine output and navigation, allowing the military to permanently eliminate the navigator and flight engineer roles, safely reducing the required crew size. The sheer mechanical output of the new propulsion system allows the J model to lift 164,000 pounds off the runway with a 41% shorter takeoff roll. The decision to radically upgrade the interior systems while keeping the exterior profile entirely intact confirms that the 1951 aerodynamic shape was already optimal. Today, the modernized C-130J fleet maintains strict operational dominance in global tactical airlift. It does face emerging market threats. Newer competing airlifters like the Airbus A400M and the jet-powered Embraer C390 are securing export contracts. To keep older legacy C-130s competitive against these new platforms, militaries utilize an economic strategy called the Service Life Extension Program, or SLEP. A SLEP entails stripping the aircraft down to its skeleton to completely replace the primary center wing box and swap out fatigued structural metal. This structural overhaul adds decades to the airframe's life, at a fraction of the massive budgetary burden required to procure an entirely new fleet of turbofan transports. The ultimate engineering lesson of the Hercules is simple. Physical geometry dictates utility. Continuous rolling upgrades and structural life extensions will keep the J model flying well into the 2040s and likely beyond. The aerospace industry frequently prioritizes designing the next complex platform. The C-130 proves that true innovation requires the discipline to recognize a perfect structural foundation and leave it alone. Pause the video here to review the full list of technical references and source materials cited in this analysis.